Hi, I showed you examples of differential expression analysis using edgeR or dissec, and you can try something else. But what is remarkable, whenever we do this DEC analysis, we compare groups. It can be A and B, it can be male-female, it can be young and old. But then you can say, hey, young and old is age, and age is a continuous variable. So why don't we use real ages for differential gene expression analysis? The problem is, as usual, in details. If, for instance, we take edgeR protocol, we declare DJ list where we mention what samples are and what the count data table is about, and then we inquire samples. And in this particular case, yes, we have a discrete column sex, for instance, group young and old, and we have continuous variables age. And then we go through normalizations and filtering, etc., to this key line design, where we usually say group and sex, and then inquire design, and then we say, okay, we are ready to compare group old with group young with a correction for sex. If, for instance, we say age, which is continuous variable, and go into design, then what happens is that every age is taken as a group with a single column. It will not work. In the case of regular regression modeling, we can easily combine continuous variables with the discrete variable like gender and add some noise and run a model, LM, which is a prototype of GLM and others, and it will work all nicely and give you the results, plot the model and the fit. The problem with edgeR is that the model matrix function is not expecting absolute ages. It only expects discrete or categorical data, which will allow splitting your data on groups. If you think dissec is better, it is not. We declare our model matrix in this line, but whenever you go further to the data processing and results part, you will see that the age was treated as groups again. It doesn't understand that you want to use age as a continuous variable. But there are good news as well. If you look into edgeR, user's guide, menu and tutorials to the end, you come across time course RNA-seq experiment of Drosophila. In this chapter, they give example how to use time for differential expression using edgeR protocol. They deal with the embryonic development of Drosophila. It's actually very good data. Embryos, then larvae, then adult flies. The example covers only embryos, which are regularly taken with a 2 days interval. You can see common lines like filtering and normalization, but then some other lines which are new, like poly hours, etc., etc. I copy-pasted lines from the user's guide. The beginning is, as usual, we need the counts table and the sample table. What is interesting here that we use some tech reports, which is very useful function. The problem with this is that count table is huge. It has 147 columns of all kinds, including technical replicates, and in order to collapse those replicates, it's easier to see it in a sample table. We need embryos of particular kind only one time. You condense it using some tech reports. Next, we create a time scale. We artificially generate time and take only first 12 columns, and then we declare in DJ list pulled counts table on the first 12 columns, and time is 2 hours, 4 hours, up to 24 hours. It's a simple experiment, only one factor. Let's try that simple business first. Then, as usual, we filter by expression, and then we add the annotation, because we need the real gene names probably. I modified this part through select and replace. All genes in Flybase are in the same order as in accounts. Then we normalize, then we have a look into this NDS, which is not so relevant. And this is new. So what we will do now, we will not do a matrix fit and GLM fit to our group, we will do a fit to the polynomial. With your hours scale, you will either generate orthogonal polynomials of a degree of 3, means linear quadratic cubic component, or it will be spline function of the same degree. The entire math is very complicated, but you can simplify it for yourself. Just imagine that you will compare your individual gene expressions to this design. You will try to fit those expressions to the polynomial function or to the spline function. That's basically the trick. So pay attention that they give you two options. You either use this polynomial or you use a spline function. There is a little, not that big, but still a little difference in the results. And now we go as usual, estimate dispersion, do plot BCV, do GLM fit, declaring our design. Then we ask for what for fit we have. And this is unusual because in this particular case, with intercept available, so it tests every gene to the polynomial equation with the linear quadratic cubic coefficients and intercept, and this is what fit result is. And now we do TT and tops, and this is more or less the end product. So you can, at this stage, you can run polytops and cubic tops depending how you define X and compare them. Why not? Let's declare polytops as tops. And now we repeat this spline function. Now we get tops out of spline. Now we can call Euler and do the plot. And you see that there are 6,000 differentially expressed genes in common, depending how you define X. But then there is a little fraction of the genes which are not the same. And you can run Euler instead of Venn, then it's even more obvious how similar the results are. You can also inquire for head tops, and then see that unlike to the regular differential expression table, there is no log FC in a usual sense. There is log FC to the coefficients of the spline function, so it does not characterize how they actually change. And this is the problem which requires additional illustrations. Whereas in a regular group comparison, you are happy with the grouping results on going up and going down. Here you need something like expression profiles through the time. So we can approach it in different ways, and first we can check how observed and fitted data are compared to one another. And these are examples from the user's guide that they suggest, okay, you can check first 9 genes out of your list and enjoy the fitting curves and see how nicely they fit to one another. But of course you would not be happy with this because you want them all, or at least some considerable part of it. Although I must admit 6,000 differentially expressed genes which depend on age is a little bit too much for the regular computer. There are computational problems attached. And therefore, to visualize all these profiles, I take only first 500, then check the input, and then say split me all this stuff on 9 clusters. Pay attention that I recruit this library tmixclust. The tutorial is available in Bioconductor. It's not very big, and the major product out of it is that classifying time profiles for gene expressions into groups. Be careful with these numbers. 500 is probably maximum for 9 clusters. If you have less clusters, then you have to decrease this number. So the ratio number of genes to clusters should not be too big. It took me a few minutes to wait for the result. Now we can enjoy the silhouette, which tells you number of genes in every group out of 500. It's not equal. For instance, number 9 is the biggest group, number 4 is the smallest, only 9 profiles, and so on. Then I like this palette invented by edgeR, and I modified it a bit because it was 7, now I need 9 colors. With this package I can run the plot only one at a time. So this is a cluster 1, for instance. This is the cluster 2. No, it's not fully homogeneous, but it's reasonably okay. Clustering of patterns is a special problem, so don't expect an ideal solution. We can also ask for number 4, which is the smallest one. That's the smallest, okay. And the biggest. Alright, so the biggest is somewhat uncertain. It's changing in time, but still not clear how. So it's probably going up and down. Most of it, maybe not. I also try to classify all these profiles to do similarity first. It's a MDS plot based on similarity. And then I try to cluster them using hierarchical clustering, using coordinates as a measure of similarity. I didn't promise you to write a chapter into your manuscript, so it's all my solution which can be further improved. And now, after clustering with hclust method complete and distances are Euclidean, we split all this variety of 500 genes on a separate clusters, and in order to make sure we understand what is what, then I add the cluster colors in the middle, and you can see that they are pretty random. They are not following the circle or the oval. It's this number 1, and this is 2, and this is 3, and this is 4, and you see it's going all directions. Now we can visualize one cluster using our previous approach, or we do it all together. Then we have to find highs and lows first for the right scales, and then we simply put a plot and lines function in a loop, and then we do this. Scales are needed for a little element, it's for alpha coloring. So now I hope you are more satisfied with the result. It's not all 6000, but at least it's 10% of it, where you can see all clusters, and these tiny dots in the background is the average of the profile. They might feel redundant or not, it's up to you to decide. You see that cluster 9 is the least fortunate because it's certainly heterogeneous. The rest are pretty homogeneous. And after this, what you have to do at the end is this: get tops and clusters, merge them together. So then when you ask for final result table, you have your names, you have this strange log FCs, although you have p-value edgeR. But this is essential. These are the clusters. So they're all grouped in 9 different clusters, and these are visuals of it. With this, the mission is more or less accomplished. We found a way of using real edges, and we got our differentially expressed genes in real time using edgeR. That's the story.